So, welcome back to session 2 of the 2022 miniKanren workshop. Up first is Byrd presenting a virtual tutorial entitled A Tutorial Reconstruction of miniKanren with Constraints. Take it away, Will.
Thank you, Jason. All right, well, welcome everyone to 2022 miniKanren workshop. I'm excited to be here. Nada, Min, and I ran the first one of these a few years ago, and it's great to see it keep going, even in the midst of pandemics and all that. Today, I'm going to present a paper that I've worked on with Bharathi Joshi, who's the main author, who unfortunately isn't able to present today. So I will do my best to present his work. And so I'm going to try to give as much context as possible. Okay, so let me see if I can share here. And okay. All right, great. That seems to be working. So here is our paper, a tutorial reconstruction of miniKanren with constraints. And so this is Bharathi at IIIT Hyderabad. And I'm Will Byrd at University of Alabama at Birmingham. So what is this paper about? Well, this paper really is about trying to help people understand what has probably become sort of the poster child of miniKanren examples. And by that, what I mean is the simple relational interpreter. So an interpreter for a subset scheme written as a relation. And if you haven't seen that, if you're at the miniKanren workshop, you probably have seen this. But in case you haven't, let me just give the obligatory short demo showing the capabilities of this interpreter. So I'm starting up a scheme interpreter. I've loaded miniKanren and also this little subset of scheme interpreter written in miniKanren as a relation, which we call a relational interpreter. And I can play some games with it. So in scheme, we have a function called eval. It's actually this REPL. You see the caret is using a val internally. So if I do something like say plus 3, 4, that expression gets evaluated. I can also put a quote in front of plus 3, 4. And in scheme or Lisp or Racket, the quote means do not evaluate the following expression. Instead, just return the expression as a datum. And so we get back a list of length 3, whose car or whose first element is a symbol plus, and then we have the numbers 3 or 4. So we can add a quote to some expression to prevent evaluation. And we can also go the other way. We can use the eval function on a quoted expression to evaluate it. Okay, so that's what eval does. Eval takes an expression or it takes data representing an expression and then it evaluates it to give us the value. And I could do something like have a list, a call to list of quote cat, quote dog. And if I evaluate that quoted data, then I get back the list cat dog, that sort of thing. So the idea of this relational scheme interpreter is that instead of eval, we have the miniKanren version of eval. Instead of eval being a one place function that takes a datum and returns the value of that datum, or basically a quoted expression, Instead of that, we're going to have a two-place expression, or a two-place relation that takes both an expression and the expected value. And the great thing is, of course, because it's a relation, we can play games with logic variables. So in particular, I can do a run query, and I can do something like, here we're calling it eval expo, eval expression. I can give it an expression like list, quote, I, quote, love, quote, miniKanren', and I can give it the environment, the initial environment. In this case, I'll say has no bindings, it's empty. And then I can say that we want the value of this expression when we evaluate it to be Q. And if I run that, I see that we get back a list containing a single value, and that single value is the list I love miniKanren'. Of course, what makes it more interesting than just a traditional evaluator is I can move that logic variable Q to be in the expression position instead of the value position. And I can take this expected value and put it in the third position. So we have the expression position, the environment position, and the value position. So I can put in the quoted list. I love miniKanren', and I can ask the relational evaluator or relational scheme interpreter produce an expression that, when evaluated, gives me the list I love miniKanren'. The first such expression is pretty simple. It's just quote of that list. But the great thing, of course, is I can ask for more. So I can say, give me 99 expressions. And here's just one. I'll just grab this. We have some side conditions, which I'll ignore, saying what has to be a symbol and so forth. Um, I get this somewhat complicated looking expression with lists and quoted things and so forth. And if I evaluate that, I get back I love miniKanren'. If I wanted to, I could clean this up and put in some, some names here about that, and I get the same thing. Okay, so this allows me to play interesting games, and the sort of traditional, really fun example that we show is basically a puzzle that John McCarthy gave in his micro manual for Lisp. And he talks about writing a little interpreter for Lisp. And he has this puzzle, difficult mathematical type exercise. Find a list E such that the value of E, that is when you evaluate it with eval, is equal to E. Okay, so the name of such a program or such an expression E is a Quine, after Douglas Hofstadter, coined the term Quine after the logician. So if we wanted to, we could try doing McCarthy's puzzle directly, and it doesn't really matter here what the environment is. We'll say it's the empty environment, but we have some expression E, and we want, when we evaluate E, to get back E. And if we run it, we get this kind of weird looking thing with the side condition. And if I want to, basically the side condition just says that this underscore zero placeholder represents some variable. I'll make it a little easier to read by replacing that with X. If I evaluate that expression, I get it back. I get back the same value. So this is a Quine. In fact, this is the canonical Lisp Quine. And so this is why we call the particular relational interpreter the Quine generating relational interpreter. So this program is, sort of the gateway drug to miniKanren' for many people. I think this is the program that gets people excited, or at least got us as developers of miniKanren' really excited. Dan Friedman and I gave a talk at ClojureConj, as the second ClojureConj, and Stu Holloway pointed out after we demoed an early relational interpreter that we should be able to use it to generate quines, and that led to a bunch of additional work. And then that in turn led to being able to generate, do program synthesis and do things like generate, append, synthesize recursive programs from examples and so forth. That Michael Ballantyne and Greg Rosenblatt and Nada Min and many other people, Rob Zinkoff and so forth, have been working with us on for many years. So this program is really the sort of the essence, the core of what's really cool about relational style programming, in my opinion. Now, there's a paper that Dan Friedman and Eric Holk and I wrote for Scheme Workshop. This is in 2012, and it's called miniKanren' Live and Untagged, Quine Generation via Relational Interpreters. This is a programming Perl. And this was the paper that introduced the interpreter I just showed. Now, the nice thing about the paper is I think it's fairly easy to understand how the relational interpreter is written and how that works. The downside of it is that this relational interpreter uses constraints that go beyond unification. So we have operators in the language, in fact, you can see it here, that are not just equal equal. So here's our equal equal and fresh and run star, things that are familiar to any miniKanren programmer. But you can also see we have absento, symbolo, this equal 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 with a slash through it, which is disequality constraint. There's also a numbero constraint. So there are additional constraints that you have to understand how to use in order to write the relational interpreter. I don't think they're so hard to learn how to use these constraints. Something like symbolo and numbero are basically type constraints, runtime type constraints. Those are pretty easy to use. Disequality constraint is relatively easy to understand if you can understand unification. It's maybe slightly more complicated to understand. Absentos may be slightly more complicated to understand, but these aren't so hard to understand. However, there's a bigger problem, and that problem has to do with understanding the implementation. Now, originally, Oleg Kislyak worked with Dan Friedman, and based on many years of work from Dan, they put together a logic programming language, and they had this famous paper on was a monad T, this monad for backtracking interleaving search. They've written with Amr Sabri and Changchia Shan, talk about sort of the internals of the search. And then there was the first edition of the Reason Schemer, of course, that gave an implementation. However, the implementations of Kanrens or miniKanrens, I think, were quite difficult to understand until Jason Heeman and Dan Friedman wrote this remarkable paper for a system called microKanren. And the great thing about this paper is it explains in a tutorial way how you could build your own little logic programming system, your own little miniKanren, including going through different versions of the search. You can see here that in yellow we have versions of the search that are basically going to be updated. And the great thing is at the end you can see the amount of code you have is very small. And this paper has been a fantastic success. Probably most of the people watching the video, or at least the people attending the miniKanren workshop, have implemented their own microKanren based on this paper. And so at this point, it's sort of a rite of passage for anyone interested in miniKanren to implement their own microKanren core, so they can play around with unification and and the interleaving search and so forth. So that's great. Now, the thing that's a little tricky is that when someone understands the microKanren, they implement unification, and that's it. That's the only constraint that's discussed in this paper. If they really want to get into the fancy stuff, then what they really want to do, if they want to get into full program synthesis, is understand something like Michael Ballantyne's faster miniKanren implementation. So this is the fastest implementation of miniKanren in Scheme or Racket. And this is the implementation, or the basis of the implementation, I should say, for the 2017 ICFP Perl that talks about program synthesis and generating things like append, recursive programs from example. So this paper, which talks about append, which I think is the other great example of synthesis that seems to inspire people in terms of using an interpreter. This paper uses the same constraints as in the 2012 Quine's paper. It uses disequality, absento, symbolo, and numbero. So those are the additional 4 constraints that we use when adding basic functionality for a relational interpreter, in addition to unification, which is the basis for equal. There are all sorts of other constraints we could add. We could add various arithmetic constraints, for example, or nominal unification constraints. But those 4 are really the ones that you need to start playing around with things like Quine's, to start playing around with things like the interpreter that can handle append and so forth. Now, the thing about this faster miniKanren implementation is it's got a bunch of optimizations in it. And it uses some clever techniques, uses things like attributed variables, where the logic variables themselves have constraints associated with them that can make the implementation much more efficient. It has an efficient implementation of the substitution and things like that. But there's a trade-off in that this additional efficiency can make the implementation harder to understand. There's a little optimization in this code having to do with, for example, using a safe mutation internally for logic variables that are assigned between the time they're introduced with the fresh and by the time there's a decision to be made with a conde, if there's a unification that gives a value to that variable, it turns out that faster miniKanren does an optimization, a safe optimization involving a side effect or a mutation that can avoid having to add that logic variable to the substitution, for example. So there's things like that optimization in the faster miniKanren implementation that makes it a little tricky to understand this code. So the idea that Bharathi had was it may be easier before you try to dive into this code. And in fact, Greg Rosenblatt made a number of changes to faster miniKanren to make the code faster for synthesis. Before you dive into Greg's code, you definitely want to understand Michael Ballantyne's faster miniKanren code. And before you get into the faster miniKanren code, you probably want to understand how those 4 constraints are implemented. And those 4 constraints are defined in this Quine generating interpreter paper. And there's an appendix in the very back. In addition to telling you the semantics, or the informal semantics of those constraints, there are a number of appendices. So here's the interpreter in Appendix A, And then there is relational arithmetic system, of course. But there is an appendix which has the optimization or the implementation of the whole system, which is right here. The miniKanren implementation, Appendix D. There are a few comments, but for the most part, it's basically a code dump. So this paper is not really about explaining the code. In fact, you can see here that these 2 pages have very little explanation. It's basically just code, and it's sort of up to the reader to try to figure this stuff out. And the reifier gets a few comments, but that's about it. So this is the code that really is probably the easiest way to understand the implementation of the constraints, but there's not a lot of description to go with it. So what Bharathi thought would be nice would be to do something sort of in the vein of the microKanren paper, but for this miniKanren extended with constraints from the 2012 Quine's interpreter paper. And he also wanted to show that there's basically a 4-part recipe that you can use to add a new constraint to miniKanren. So part of the idea of the paper is once you understand how to add these 4 constraints, you could add additional constraints to the resulting implementation. And in fact, you could invent your own constraints and add them. And there's this 4-part or 4-step recipe that tells you how to add these types of constraints. And each of the constraints that are described in this paper follows the recipe. So the idea is that by the time you've implemented the entire paper or gone through the whole code in the paper, not only do you understand how those 4 constraints works and have a working implementation where you can play around with program synthesis, but you also should have internalized the techniques used to implement a new constraint. And now you can stand on your own and start playing with constraints. There is, however, an important difference between this paper and the microKanren paper. And in fact, I'm not even sure if we're going to keep this title at the end, but the main difference is the microKanren paper really, I think, is a tutorial reconstruction where, for example, when you're trying to understand search, microKanren paper will implement a very simple depth first search first, and might implement a finite search and so forth, and then we'll extend or make the search more sophisticated after showing you limitations of the existing implementation. Whereas for this paper, it's not trying to build up a story in the same way. Rather, this is really the code from the 2012 Quine generating interpreter appendix D. It's that exact code with commentary. So it's really more of a commentary of the code along with describing how this 4-part recipe can be used to implement the constraints. And so that's the idea behind this paper. And the hope is that this paper can serve as a bridge between the microKanren implementation and something like faster miniKanren, which has additional efficiencies that are really needed for something like program synthesis. I should also point out that there's the code from the Reason Schemer second edition is available on GitHub, which is basically this code is basically a modified version of the microKanren code. So that's another starting point as well. But regardless of the starting point, once people understand the ideas of microKanren or from the second edition of Reason Schemer, they should then be able to read this paper And the paper does assume that people have read the microKanren paper. And from that point on, people should be able to read the faster miniKanren code and understand it. I think that code has enough comments and description that if you understand how these four constraints are implemented, how the reifier is implemented, and so forth, you should be able to go and understand the faster miniKanren. Okay. So with that, I think I am ready to take any questions.